Hello everyone. Today we're going to look at applications to the integration with work and average value. So we're going to start with work. If the force, which we call F, that's applied to an object is constant, then the work, which is W, that's done on the object is given by W equals F times D, where D is the distance the object has moved. So work equals force times distance. You've probably seen that if you've taken a physics course before. What we're going to do, though, is we're going to look at situations where the force is not constant. And if it's not constant, we can use integration to find the work done. So for our problems, we're going to assume that the force is a function of the distance. It can be functions of other things, but for us, we're going to look at force being a function of the distance. If that's the case, then all we have to do is integrate over the function and we'll get the work. So the work is the integral from a to b of f of x dx. So a and b are the distances that the object has moved, right? A and b are values of x. The most famous example is Hooke's law. Hooke's law states that the force applied to a spring to stretch it a distance of x units is F equals k times x for some constant k, and the k depends on the properties of the spring. So, for example, if it takes 20 units of force to stretch a spring of natural length 8 inches to 10 inches, find the work done in stretching it from 10 inches to 12 inches. So first, we need to use Hooke's law to find k. So F equals k times x. F is the force is 20. The x is 2. So again, x is the distance that we've stretched it. We've gone from 8 inches to 10 inches, so we've stretched it 2 inches. So k is 2, and then x is 2, and we're looking for k. So we solve for k, we get k is 10. We're going to plug that into our work formula. So work equals the integral from 2 to 4. Again, the distance being stretched. So from 8 to 10 is 2. From 8 to 12 is 4. So we're not integrating from 10 to 12. We're integrating from 2 to 4, the distance stretched. And then of the integral of k times x, so 10x dx. The integration on this is really nice. You're always just going to get k over 2x squared. So we have 5x squared from 2 to 4. And we get 60. And then it's whatever the units of work is, which depends on the units of force. We're not going to worry too much about the units, so I'm just going to put units. So let's try another one. Suppose you have a string of natural length 50 centimeters. The force required to stretch it another 20 centimeters is 35 units of force. Find the work done in stretching this spring from 55 centimeters to 65 centimeters. So again, we start with Hooke's law. So the force was 35. The amount stretched was 20, and again, we're looking for k. So I'm just going to simplify 35 over 20 and get 7/4. Make sure that you don't round in here, so keep it as a fraction in your problems. You want to make sure that you're keeping all of the values in there. 7 divided by 4 isn't a bad fraction, but if it was, say, 4/7, you want to make sure you keep that whole 4/7 and don't round it all. So we're going to leave it as 7/4. Again, the work is going to be the integral from 5 to 15. So from 50 to 55 is the 5, and then 65 to 50 is the 15. So again, it's really important that you remember that x is the distance stretched and not the length of the spring. So we're integrating from 5 to 15 of 7/4 x dx. Again, we're just going to take our k divided by 2 and multiply by x squared. So we have 7/8 x squared from 5 to 15. And if you do that out, you should be getting 175, again, whatever the units of the work is. Okay, so it's not always going to be a spring. So we have another example here. Suppose the force on an object is given by F equals x to the 2/3, where x is the distance traveled by the object. Find the work done in moving the object 8 units. So force is a function of distance, right? Again, x is the distance. So to set up the work, we're just going to integrate. And we integrate from 0 to 8 because that's the distance the object has moved, and then we're integrating our f, which is x to the 2/3. If we do that, remember we add 1 to the exponent, so we get x to the 5/3. Dividing by 5/3 is multiplying by 3/5. So we have 3/5 x to the 5/3 from 0 to 8. If we do that out, we should be getting 96/5, which is 19.2, and again, whatever the units of the work is. So now we're going to look at average value. If we wanted to find the average value of a certain number of things, then of course we add them up and divide by how many there are. However, we're going to look at trying to find the average of something that's continuously changing. So what if I wanted to find something like the average temperature over a certain time? One way to do that would be to take the temperature every hour and then find the average of those 24 temperatures. Or I could take the temperature every half hour and find the average of those 48 temperatures. Or I could take it every 15 minutes, or every 5 minutes, or every minute, or every 30 seconds, or every second, or every millisecond, or every, 10,000th of a second. So I could keep doing that, and I could make it more and more precise. The more temperatures I take, the more units I have. But if I want to find the true average over, again, something that's changing continuously, we're going to involve an integral. The integral is fairly straightforward. We take the integral of the function, so the integral from a to b of f of x dx, and then we divide it by the length of the interval. So we multiply by 1 over b minus a. Okay, so remember, an integration is a sum. So this does make sense to find the average. We're summing up everything that we can, just it's an infinite sum, so it's an integral. And then we're dividing by the length of the interval versus the number of things. So it should at least look familiar to be an average. So we're going to do some examples. So the temperature in degrees Celsius over a given day is given roughly by capital T for temperature equals 0.001 lowercase t to the 4th minus 0.280 t squared plus 25, where lowercase t is a number of hours from noon. So t goes from -12 to 12. We want to find the average temperature during the day. So we're going to set it up. It's the integral, it's 1 times 12 minus -12, so 1 over b minus a. The integral from -12 to 12 of our, of our function, dt, where t is our variable. So our fraction becomes 1 over 24, and then if we integrate, we get the following, and we're going to evaluate it from -12 to 12. And if you want, you might want to pause the video and make sure that this is the integral you get when you do it out, and then you might want to find the actual value and then make sure it's the same as what I get. So, we plug in our 12, we plug in our -12, we subtract the 2, and we get 15.7 degrees Celsius. The units are always the units of the original function, which hopefully makes sense. The average temperature should be a temperature. You've got, this guy is in temperature, this is in hours, this is in 1 over hours, so the hours cancel, and we're left with the temperature. You always want to make sure that your units make sense. Okay? So here they do. So let's try another one. Find the average value of cosine of x over 0 to 2 pi. So there are no units involved with this. But the average is going to be 1 over 2 pi minus 0, so b minus a, and the integral from 0 to 2 pi of cosine x dx, The integral of cosine x is sine x, so we get 1 over 2 pi times sine x evaluated from 0 to 2 pi. And again, I would suggest you do this out first and then come back to the video to make sure you're getting the same answer. Okay. So when we do it out, we should be getting 0 for both of them. Sine of 0 is 0, sine of 2 pi is also 0. So we end up with a 0. The average value of cosine of x is 0. And if we think about it, if we draw out cosine of x, right, we get something like that from 0 to 2 pi. So 2 pi is over here. If I average that out, the positives and the negatives kind of cancel each other out. And so my average is this guy right here. Okay. Let's try one last one. Find the average value of x squared minus 2 over the interval 4 to 8. So again, we're going to take 1 over 8 minus 4 and then integrate across 4 to 8 of x squared minus 2 dx. The biggest mistake that I see people doing is they're forgetting this guy over here. So don't forget, if you don't divide by anything, if you're just taking the integral, all you're doing is finding the total change in it. So the average isn't the same as the total change. It's the total change divided by the length of the interval. So don't forget about that 1 over b minus a part. Again, the integration here is not too difficult. So we get the following. And then when I do it out, I get 1 over 4 times 424 over 3. I want to simplify it. Again, make sure that you keep the exact answer. Don't round in the middle. We get 106 over 3. Right, that's a repeating decimal. You want to make sure you have all of that in there. So just leave it as 106 over 3. Okay, so we've done work. We've done average value. So try them out, make sure it makes sense, and let me know if you have any questions. Thanks.